4 inches.
All right. A quick example. I know I talked about expanding the logs. Like, I hope we went over enough examples on like 7 so that you are comfortable with that. I just wanted to go over maybe one quick example to make sure you're not confused on like, say like 9a. So you're just using those same log properties, but like basically in reverse. So, I'm sorry, 3. And we'll go over 10 after this. So like on this one, you'd go, well, what happens to this 2? That 2 is going to become an exponent on the log. So I have log of x squared. And how about this 3?
Log of y minus 4.
Yep, same thing. Now, don't try to get fancy. Just the thing you're taking the log of, this item here, gets raised to the 3rd power. And then I have log of a thing plus log of another thing, so that's going to turn it into log of the first thing times the second thing. And that's all there is to it. So the instructions said, write it as a single logarithm. Well, I just did that. Now if there's a single log to describe that expression. Oakley dokley?
That's all good.
And maybe one more example just for clarification's sake. So if you look at like C says 8 log of 1 over x plus log of x to the 5th. So in one like this, straight as a single log, there's basically 2 ways to go about this, but one of the main ways is to like look at this and go, what can I do with that 5? I can move the 5 outside, right? Make sense? And here, well, that's x to what power? -1. So that -1 can get moved outside. And so then what do I really have here? -8 log of x. A little bit of banana theorem. -8 bananas plus 5 bananas makes?
-3.
-3 bananas. I had some questions on this one, like, do I write this as log of x to the -3 or log of 1 over x cubed? Those would both be fine, but I'd say this is probably your best way to write it. It's probably your most simplified way to write it. Okay? Okay, so 10. 10 tells you something at the beginning.
Wait.
All your base are belong to us?
Yeah, there's a reference to that in Breath of the Wild.
All your base are belong to us. Okay. So they tell us that log base n of q is equal to 10. Which, if you wanted, you could rewrite that as n to the 10th power equals q, but that's not really going to help us a ton. Our focus here is on using the log properties to manipulate these expressions. So like, and you're supposed to be, I'm trying here to show you something that's about how logs work. So like with the first one, and it says, if this is true, if this is the one piece of information we know, then what would log base n of q squared be? In other words, what happens if you have a log value and you like square the thing you're logging? What happens to the number?
2.
It doubles it. Because watch, this 2 can get pulled outside the log, right? Does everyone understand that?
Oh, I get it now.
And then, well, how big is this number? That's 10. So 2 times 10 is 20. So the moral of the story there, each one has a moral. Well, sort of, kind of. The moral is if you are doing logs and you say you want to change something, so say you square the thing inside, that actually have the effect of doubling your result. How about B then? What's B going to be?
70.
Okay, so if you raise your quantity to the 7th power, that would multiply the result by 7. And there's other things like, let's look at C, and I'll take the rest for you. Log base n of n times q. So what do I do there? Not subtract, I have n times q, so that's going to turn into log base n of n plus log base n of q. What's log base n of n? 1. Everyone understand that?
Oh, yes.
Because n to what power gives me n? Well, n to the 1 power gives me n. And then what's log base n of q?
Q.
No?
10.
10. So the answer is 11 here. Now that's an interesting result because it tells you, what it tells you is that if you multiply your quantity by whatever the base is, you're just going to add 1 to your number. And that's actually, you guys have heard of decibels, right? Decibels. So, April, are you catching any of this stuff? Just getting in there. So with decibels, the way that works is like your you can, well, keep it simple. I'll write it like this. There's always like actually a reference value, if you're wondering. But anyway, what happens is with decibels is if you have to multiply the power of the sound by 10 to increase this value by 1 in order to get an increase of 10 decibels. So if you're looking at like the difference, say between like 80 decibels and 90 decibels is you need 10 times the power just to increase. And then how about between 90 and 100, 10 times that. So to go from 80 to 100, you got to go 10 times 10 times, actually 100 times more power. You ever looked at like a decibel chart and they'll talk about how like casually talking in a cafe is what like 50 decibels or something? Here, okay.
And then a jet engine going 130.
Yeah.
And then wasn't Krakatoa the highest decibel rate or
Here, this is really interesting because you may have seen something like this and been like, what are you talking about? Because we actually often we think so linearly, but a lot of your perception is logarithmic. So this might be hard to see, but so down here is like rustling leaves is 10 decibels, whispering is 25-ish. But if you compare say normal conversation is 60, and a jackhammer is around 120. So why is that? Is a jackhammer really just twice as loud as normal conversation? No, because to get from 60 to 120, you got to go times 10, times 10, times 10, times 10, times 10, times 10, 6 times. That's 1,000,000 times more power. So the sound involved in a jackhammer is 1,000,000 times more powerful than your quiet rocket launch. So to go from quiet conversation or normal conversation to rocket launch, you got to go up 12 levels. So that's multiplying by 10, 12 times. That's actually a trillion. That's 1 trillion times more.
Awesome. Let's just go to the rocket launch. I want to go to space. Don't care if I lose my hearing.
Okay. I was going to give you 1 or 2 more examples of using these this idea that I showed you. You can and the main properties you can use on things like 12 and 13. And I'll cover 14 tomorrow, but.
What? How's the main going?
Because that's so weird. Because the exponent thing, you
But that's not.
Who knows the answer to that? It's not a true or false though. It says evaluate. This is from 12.
True.
100.
Wait. Oh,
Because, what's 32 to the 100th power?
big.
Exactly. It's an enormous number. We don't need to calculate that. The answer to this is you're close.
Close? No. 500.
What can I do with the 100, guys?
You put it to the left and do 100.
Okay, so now I go, really, this is 100 times log base 2 of 32. Ignore the 100 for a second. Zarita, focus. Zarita, what's log base 2 of 32?
320.
No, come on, this is an easy one.
Well, I haven't been here. It's not easy.
It's 5. 2 to the 5th power is 32, okay? So this is 5. You understand that? So the answer to this was 500. So the result says, do we know what 32 to the 100th power is? No, it's a huge number. And what we've shown is that 2 to the 500th power would give me this astronomically large number. Okay? There's another thing you can look at. On 13, all right. If you didn't have this, what kind of number is this? Log base 3 of 36. Is it a nice number? Is it a whole number? Yeah, can you raise 3 up to what's 3 to the 2nd power? Okay, what's 3 to the 3rd power? And 3 to the 4th power? 81, good. So we know that this number, log base 3 of 36, is between what two numbers? Yeah, we know it's between 3 and 4, so it's 3 point something, right? It's got to be an irrational number, some weird number, right? And it's actually a transcendental number. It's a number kind of like how like pi is. Decimal, it goes on forever, doesn't repeat. How about this? 3 to what power makes 4? What kind of number is this?
In between 1.
In between 1 and 2, so 1 point something, 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 right? So what's the answer going to be? Here's where we're going to use our log properties. What can I do when I have a log minus a log? Use division, right? This is log base 3 of 36 divided by 4. So what's the answer?
3.
No.
What? Oh,
2.
2. Oh. Yeah.
It's kind of weird, right? So it turns out that these decimals must have been the exact same sequence of numbers in hindsight. So you understand? Does that make sense how you're using the log properties to? Okie dokie.
Oakley